Record. All right, folks, I think we're ready to get the afternoon session going. So Argyro and Maojie are going to start us off talking about spectra. And I think you can take it away, Argyro.
Okay, thank you. So
can you, yeah, so maybe just confirm, can you hear us on Zoom? Can someone give a thumbs up, please?
I better tell the people out here in the hallway that we're
Yeah, why
starting.
don't you do that? Yeah, I see a thumbs up. Okay, so we are good to roll. Okay.
So hello everyone. Yes, my name is Argyro, and I'm postdoc here at the University of Minnesota, and I will present spectral for transient classification, just some introduction. And what we will present today here is mainly based on what we are doing as an Apple-sided team, and also a work that we put together for the ZTF summer school. So spectroscopy, it's actually light decomposition into wavelet components and could reveal about for different objects, the velocity, the redshift, temperature, composition, and we can have more information about the different events that for those we might have alerts. For example, let's say if we have a type 1 supernovae and type 2 supernovae, one key characteristic to distinguish these two objects is, for example, if they are rich, hydrogen rich or not. So every type that we have has some specific characteristics, a unique, let's say, signature in the spectra, and this is how we can identify whether we have, let's say, STD or ATN or type 1 supernovae or type 2 supernovae. And how we can collect the spectra. So there is a spectrograph, the SEN spectrograph, and this is actually how the machine looks like, and this is attached into the telescope. So, for example, I have this from another presentation, from Michael's presentation, and this is the Palomar telescope, and here is the machine where with these we are able to collect the spectrum. And actually, the spectra that you will see also here and also with the notebook are from SED data. So as I said before, we need spectra because through them we can identify better some objects, and we can make sure that it's type 1 supernovae and it's not type 2 supernovae, let's say. So here is an example of TDs. So one characteristic that they have is that they are hydrogen rich. So we can see here this line, and in many cases is very strong. And also another characteristics of the TDs is that their spectra change through the different epochs, so they evolve. However, the spectra that I present here and every spectra that we are going to see and also in the notebooks is based on the peak from the light curve, and we are not going to use spectra from different phases of the object. So yes, so this is in the during the very peak of the photometry, but we can have also some later spectra from later in the evolution. So in these cases, we might have some more, let's say, strong lines in this region. Another example are the AGNs, active galactic nuclei. And so in those cases, we have the forbidden lines, which are the green ones. And this is like a very, very, very ATN characteristic. And also we have some borderlines for Balmer lines. So again, this is like in the earlier, let's say, phase, not later. And here we have another example, supernovae type 2p. And in this case, as you can see, the hydrogen Balmer series, these ones are very broad. We don't see a very huge peak at this phase because it's earlier spectra. And also we can see that we are almost near to have a nice peak here. And this peak is not very visible here because we need the later phase. So based on those spectra that I saw you, there is the question why time matters. So it really matters to have like a spectra follow-up if we have the images and metadata and photometry. And the reason is because if we have early spectra from an event, then we can find out similar different features that are related to the progenitor envelope, or later spectra could reveal some other features, as I showed you before. So we really need multiple spectra from different epochs during the evolution of this event. And also, we should not forget that there are transients involved, so the spectra will change over hours, days, or weeks, depending on the source that we have. And they are critical for element identification, velocity measurements, detecting short light features, and they are essential to understand the origin of the event, what's happening, and what we can also have some information on what exists in their environment, and also the environment between those and us, of course. So, for example, let's say we have a type 2 supernovae involves, and then we have strong hydrogen lines that we see that we saw before, but also the forbidden lines. Another case is if we how we can distinguish like type 1 supernovae different categories. So, for example, early spectra of type 1 supernovae B and type 1 supernovae C may be hard to distinguish them, but in the case of type 1b supernovae, we have the helium lines that emerge later in the spectrum. Also, another example is if we collect spectra again and again, and we see that this event evolves for hours to days, then we have we are more confident that this could be like a fast an F-bot or a kilonovae or soft breakout classes. So it is really important in order to perform better classification to have also the information from spectra, but not only from one epoch, but multiple epochs of the spectrum. So until now, we have the information from Benny, how we can collect the images and metadata, and how important they are in order to send the alert. Felipe introduced the photometry stuff, so we can have 3 of the 4 modalities, and so spectra is the last piece of this of what we are doing as a Poseidon team. We are trying to use all the different modalities in order to have a better classification. And for cases that we do really care, we really need more spectra. And why I'm saying that? Because we have too many transients, like maybe every day. So, but on the other hand, we have limited telescope time, and we have this machine. So we are not crazy if we want more machines, like said, in order to collect more spectra and be able to support more sources. And I didn't make this this night slide, but this was from a slide from Michael, and I really like it. So we are not crazy. We need more spectra and more spectrographs, and because, as I said before, spectra are crucial, and we need like early spectra, but also later spectra. So yes, so what we would like to do is we have the ZTF, then let's say that we have an alert, then this alert goes through brokers. I think Michael provide more information about that the previous days, and then these alerts will go through the AppleSider, and then AppleSider will classify if we have an event that we really need to support it with more spectra. So if the classification shows that this is a very nice event and we need a follow-up, then this will go through the SkyPortal. We will trigger for more spectra, and then we will come back again to the AppleSider, and AppleSider will, let's say, fix the classification, because then we will have more information about the spectrum. And how we can do that? How we do that? How we have built the spectra part classification. In order to do that, we have pre-processed the data. So we have drop invalid entries. We have account for a redshift correction. There is an interpolation in order to fix the specific length. And also we have normalized the flags. Of course, someone can, let's say, not apply the redshift correction, but have actually a network to predict the redshift instead of doing before the training. And within the AppleSider, we have adapted a complex, let's say, architecture, which is this one. But I think Maojie is not gonna show actually this architecture, but a more simplified version of it. But if you want, like, as an exercise or play when you are home, I don't know, you can, you will have the slides, and also our paper is on archive, so you can have more information, and maybe you would like to build a similar architecture and see how the results will change based on what we are gonna do today. And just to showcase how spectra, why are they so important? So here we have two different plots. The first one is with spectra, and the second one, this one, is without spectra. So this is the classification, the confusion matrix. We see that we have, for example, here, confusion between the supernovae 1 and supernovae 2, and this is because actually the main difference between them is the height of the reads of them. So in order to distinguish them, we need spectra. And as soon as we have also the modality, this modality, then we can see how the confusion matrix changes. So we have very nice classification for supernovae 1 and supernovae 2. However, you will see, like here, for PDEs, for example, there is some confusion. It's not very, let's say, thumbs up, yes, it's a TDE. And there are different reasons for this. So TDEs are rare, and it's more difficult to have more data in order to better train the network. This is one reason. And the other reason is, as I said before, for what I'm presenting here, but also what we have adapted in our pipeline currently, is that we use only spectra from the peak photometry and not later spectra. Because if I go back here, the key characteristic of the TDEs is that they really change over time. So we haven't passed this information, and we do expect that if we use multiple epochs from the spectra, then we can have an even better confusion metric, so even better classification. So just to summarize, and Maojie will take the floor and will show you how you can do the spectral classification. Spectra are very important. It's not enough just to have one spectrograph. We need more. We need multiple epochs from the spectra in order to have more information and feed the network and be more, let's say, sure about what we are giving and the classification. And yes, and you can see just from these two plots how the classification changes if we just use spectra and not let just the images, metadata, and photometry. So yes, this is what I wanted to say. Now Maojie will go through the network and give some introduction about how you can actually build spectral classification.
Okay, hello guys. Today I will talk about how to building a deep learning model. Like this is a case study in spectral classification. So in this notebook, we will take a lot of the process, how to build and train a model for the spectral classification. So we will talk through all the basic things from how the block works to how to train, how to create the pipeline. Yeah. So we will follow these steps. First, we need to download and prepare the data set. I have prepared the data set already. We need to understand how does the data set works. And then we will know all the blocks of a deep learning model. The first is we will build a model. The fifth is we'll train a model on the data. But the environment is has little bit issue, so we will build the model, but we're not trained yet. And the sixth, we will analyze based on the ONNX file we trained before. So the dataset I have prepared already, I have split them to the train vol test. And in each PT files, there will store flags and labels. Flags is the length of 4096. It will go through the normalization, the z-score normalization, and it will interpolate to spectral flex data. And it also has the labels. So here is you guys can download the data here. Yeah. And then in this one, we will show the data distribution of in the data set. Okay. So the data set, the trained data set, each type okay, the whole data set will be like 80,000 spectra. It will be a lot. So I done sampling each spectral type. So the SNIA, SNID, SNIC, SN2P, SN2B, SN2N, AGN, CV, and TDE. All the train output is 560. The test and the ball with output is 120. The TDE, it don't have enough for 120, so I put as much I can. So here it shows how much, what the number of the type of each dataset. Here we'll display the data after the normalization. Yeah, here is some sample. So this is used to check your pre-processed pipeline it works or not. So the pre-processed part is very important. So sometimes you will do some part wrong. That's why your model is trained fail later. So the pre-process part is very important during a model train. So here is the data set and the data load explanation. So the following we will show based on the PyTorch data set and the data loads. The PT, it has a X is stored is the normalized flags, and the Y is stored the labels. So in the spectral data set, so here we will load the data from the PT, and then we will load the flags, and then we will load the labels. And then this line we will use to check is anything wrong with the pre-process. So the pre-process is very important during a model training. And this line we will use to sort the class. Or if we don't have this setting, the class will just order at the data. So if you want to be more organized, it's better to like organize to the type you want it to be. And here the create data load. So in the dataset part, it only can load one of the data sets. So we have three: the train, validation, and the test. So the spectral data set only can load one of them. So we need to create a function to load three of them. So here is how we load the three: the train, val, and the test. For the train, we use the train's data to train the model's parameter. The val we will use to change the hyperparameter and use for early stopping to make sure the model is not overfitting or underfitting. So the test dataset we shouldn't use during the train process. If you use that, it will consider a data leak. And here for the train data load, the train you should use the shuffle. It makes sure the model will not remember that your data order. It will cause overfitting or data leak. The number will works. It can accelerate the way your I/O read of the file. The batch size. Yeah, its batch size is how many data you put in the model one time. Here is the training and validation log explanation. So during the train need to use a function to train the model to update the parameter. The validation is used to test the result, but here we will not update the parameter. So here is train one approach. So first, we will make the model train. And here we will store some variables like the loss, correct, and the total. The sequence is the flags, the data we put inside. The target is output, is the label of the data. And this line is to accelerate your model. Sometimes you don't need that much complexity. Yeah. So if you use this line, can store some of the GPU storage. Because sometimes your model is so big and you want to make sure your model, but you also need to make sure your model has enough batch size. So it will be a good way to save your computer storage memory. If you cause a data leak, for example, your GPU's data leak, it will leak to the memory. It will slow the training a lot. But it's not the worst case. The worst case is your GPU storage leaked, and then your memory leaked. It will run on your desk. Each epoch need to use like maybe 1 day or something. It's very slow. So you need to make sure your storage is not leak. It's very important. Here is make sure the gradient is not disappear, because sometimes your loss will be none. Yeah, so it will consider as the model damage, and it will not have any training anymore. And here we'll collect the loss when you train your whole data set of the train. And then here is store the predict of the labels. And here we'll collect how many the model predict right. And here it will calculate your in this epoch, your model's accuracy. So here we'll return the accuracy. The validate. So it starts with model evaluate. The model evaluate, it will make sure that the parameter will not update. The validate is only used in the validate data set and the test data set. So here the torch, no gradients. That means it's no parameter updates. So here is just like the train one approach. We just put the sequence inside and the label inside and to see the result. Here we also use the auto cast, like to try to make the model run faster. Here we also collect the accuracy. And here also we will calculate the F1. And we use the macro F1. Macro F1 use when your data is imbalanced. So if your data like your SNIA has like 9,000 data, your TD only have like 200, it's better to use macro F1. Another one is this one. This one use when your data don't have a very big imbalance. Because if your data is imbalanced, you use this one, will make the score main focus on the main percent data. So here we should use the macro F1 instead. And here it just shows the confused matrix. It will return the raw loss, raw accuracy, and raw F1 macro. Here is some basic knowledge of the data training. There are some common loss functions. So in this notebook, we only show some used during the classification and regression. we will not cover like the regenerate or like the mask, or like generated mask or something like that. Or like the VAE, the autoencoder. This loss we will not include in this notebook, but you guys can search online to explore more. So the first one is a binary cross entropy. The symbol we call it BCE. It's used for like binary classification. So the output should be like the probability like from 0 to 1. This will all use the sigma. Yeah. So if you use BCE loss in the so if you use the BCE loss, it will not include the sigma. You need the code by yourself. But if you use the BCE with the logic loss, it will include the sigma. So it's better you just use the BCE with logic loss. Another one is cross entropy loss. It's used during the multiple class classification. Like we have a large target class, just like our Spectra classification. Yeah, they will use the log softmax. It will predict each label's possibility. So they will choose the highest one to output. So sometimes if your model don't have like the very good accuracy, but you still want it, they give you some result, you can choose the top 3 softmax possibility. Yeah, sometimes, yeah, it can make sure the model at least has something output. Another one is regression losses. Compared to the classification, which is classify the different class, regression loss will predict the numbers, just like the redshift predicts, or the temperature predicts, like the finance predicts. It's used for the predict the numbers. So there is 2 normal error we will use to. The first one is MSE, mean squared error. In general, we will just use this one. It's a general for the general regression tasks. It's very sensitive to the outliers. It will penalize the large errors more. Yeah, in the PyTorch, you just use the NNMSE loss. And another one is the mean absolute error, MAE. It is used for the case when it's the regression with outliers. It's more robust about to the outliers. It's less sensitive to large errors than the MSE. So in the PyTorch, if you want to use is NNL1 loss. Here is a summary chart table. Here is a summary table for you to choose which one you need to use. So after we talk about loss, another thing is optimizer and scheduler. Optimizer is used to update the model weight, update the parameter. The scheduler is like adjust the LR, the learning rate for the model. So here is the training step flow. In the forward pass, we get like if we train the models and we get the outputs, and then we will use the loss we talk in here to calculate the loss in this approach. And then we'll calculate the loss, and loss will to the backward part. It will calculate the gradient. So the optimizer get the gradients. It will go to update the parameter, and then the LR schedule state will go to update to next steps. So the relationship between loss, gradient, optimizer, and scheduler is just like when you use the Google map. Just like if there is a target, you have you have a place you want to go. The loss is like from your right now position to your goal position, the distance between them. And then the gradients will tell you what's the direction you should go. They will navigation which direction you need to go. And the optimizer is like when you are drive the car, you use that to turn the wheels to follow the path. And scheduler is used to like how fast you will go to that goal place. So just like here say, if your schedule provide very error, like big error, the learning rate, yes, it will go to the position very fast. But sometimes they will go to the goal position, but then since you are so fast, you will go through that. And then so not always the error is bigger is better. So maybe it's like this time we a little bit slow, a little bit slow, and then just to the target position. So here is some common optimizer. SGD with momental and the ADAM and ADM dot. The SGD it don't have the momental and it's not adaptive AR. It's used like for very basic models. Its advantage is very simple, but the coverage is very slow. So it's only used when you use some very small models or like used for the baseline compression. The SGD with momental. So it's just the SGD has a momental. It will add the velocity to the SGD to smooth and accelerate updates. The advantage is it will have a strong generalization. Yeah, but the bad part is it's very sensitive about to the learning rate and the momentum. So it's used for like the very, very large CNN models or for the image classification. So ADM is right now most popular optimizer we used. So it will combine the momental and the per parameter adaptive LR. The advantage is very fast to coverage and it's very easy to use. But sometimes it maybe will overfit. And it will have the worst generalization. It will show is like your train is like 95 accuracy, but your validation have only like the 80, 85, something like that. So in general, we use for NLP, like the small data. Yeah. And the ADAM dot, it's just the ADM with the weight decay. It can show some like the disadvantage of ADM, which is overfitting. It can have like better regularization. It's fast and stable. It's very strong for right now's model deepness. But disadvantage is just it will use higher memory, but it's okay. Yeah. So right now some model like transformers, VIT, and some new model in the ImageNet 22K always use the ADM dot. So right now, in general, we will just use ADMW. It always in general it has a better result. But if you train a data or try to find a better result, you should try all of them and compare which one has better one. And here we show 8 learning schedules. The first one is a constant AR schedule. It's just never change. It's just the same AR from the start to the end. the step ARR schedule is like it reduce when you like we will say like 1,000 steps or epoch, we will reduce the ARR. We will reduce the ARR again in 2000. So it's just like, okay, the target position is there. We want to go there. So at the beginning, we will use very fast velocity to go there. But later, when we close to there, we can use a very slow. We use very slow velocity to close to the target position. So this is the goal of the next several ARR schedule. It's always better than just use the same ARR forever. Yeah, and then the expulsion ARR schedule, it will have the smooth ARR than the step ARR and the multi-step ARR. And then is the cosine annually ARR. You can see it's more smooth. It's more smooth than exponent ARR. Another one is the cosine annually with warm restart. So it's like we set a stack. So the ARR will find the biggest one to go to the lowest part. And then when we got the epoch, we'll go back to the height and go back again and go up to the highest one and go back again. It can find the better result, but you need let train longer. And the cosine annually warm restarts. It tries to jump from the local best position. It's just like a mountain. Here is a mountain. We thought the model will start this position is the lowest one, but might be if you cross this mountain, another mountain is height, and we go down again, we can find a better one. So the cosine annually warm restarts is used for this. It will jump to the local best to try to find the global best position, best target. So this is the summary chart of different ARR. The first one is the constant ARR. It will keep the learning rate constant. It's used for the simple models and you want to do debugging. Because sometimes it's because your ARR has some issue. That's why you didn't get a good result. So in general, when you try to build a model or do something, you should start on the very simple start to make sure every part works. It's not like give a negative influence. The step ARR, it will decay the ARR every fixed number epoch. So it's used for the classic CNN like resonate and rigid. You can see this model is very old. It come out like 2018. It's like 7 years ago. The multi-step ARR is just like similar like step ARR. It's not like very big difference. And exponential ARR, it use Y to use a gamma to reduce the ARR every epoch. It is used for the small models or fast coverage. And then is a cosine annually ARR. It will cosine decay to the minimum part. It will have the T max and the minimum. It's just from the up to the lowest one, but it's very smooth. It's used during the transformers or vision models. The cosine annually warm restart is just a plus version of cosine annually ARR. It will have a multiple cosine decays with restarts. It will have T0, T multiple, and minimal. It uses the cosine waves with restarts. It is used for the pre-train the large models. It keeps the local minimum. The cyclic ARR. It is oscillated between base ARR and max ARR. And then it used for the model like NLP, large scale training. Yeah. And the 1 cycle LR, it increase, then sharply decrease LR. Yeah, it used for the modern DNS transverse learning or fine tuning. Some people will say like ADMW and ADA, this will adaptive the LR. But here it will change the LR again. Why? It's because this one is for the global LR, and this one is for the small LR doing each approach. So it will just multiple together. It will have a better result. Right now, the mainline train function explained. So first, it will set the seeds. Set the seeds is very important when you train a model. It can make sure the model it will make sure the model has the same results when you train 2 times. If you don't set the seed, it will have different results. It's very because different seeds will have different results. If you do the model compression, you need to set the seed. It can make sure have the, like a fair compression. And the device and get the device. It's just used to get your data, get the device you will run the model. If you have the CUDA, you will just use CUDA. If you don't, it will run on your CPU. It will be very slow. And then we will load the data. And then here it will it will load the model structure. And then here is optimizer. Here use the AMW. In general, it will have a better result, but you need to test. And this scheduler is not the same like the one we talked before. This one is like a compose. We can compose different like the AR scheduler during your training. So here we'll do a warm up. It will start from very slow point to the normal point. And then after that, so we can say the warm up approach, the 5 flow. So it will from very small part, like the here say. It will from the very small part to go to the original, to go to your LR you set, to make sure at the beginning the model can train stable. After that, we will just use a cosine annually warm restarts to make sure it will not get a local best, local loss minimum. And then here we will use the CE because we have different targets. And here is the early stop. Early stop is very important. It can make sure your model will not overfitting. They will test on your validate data state to make sure like we train like 5 or like 10 approach, and then if the before 5 approach the validate never improved. So right now we know okay, before the 5th approach is the best part. We shouldn't train longer. Train longer, maybe it will just overfitting the validate. It's not good for the model. Sometimes it's considered data leak too. After the early stop part, we will just test on the final test, the final data state. We will never touch before. The data, the parameter, the model never know this data. It's try to know the data in real life. So here is some configuration. And then if you state like the batch size and LR, they have an equation. Like if you reduce half of your batch size, like if we from 128 to reduce to 64, our learning rate should be also reduced to half. In general, you have a good result. It can make you not wrong, not like turn the model again. It will be fast for you.
Other, please. Okay. Yes. So yes, I think we can start again. And yes.
Yeah. Okay, let's start again. So after we talk about the pipeline, how to training, how to build the training pipeline, and right now we will talk about some basic knowledge about the deep learning models. So the first one is a convolution. Convolution is a fundamental operation in deep learning that applies the learnable filters to extract local patterns from input sequence or signals. So this is a GIF for how does it works. So this equation is how to calculate the output data length. So it's the input length plus 2 pattern size minus kernel, and then divide straight and then add 1. So here is an example. Let's say the input channel is 1, output channel is 4, kernel size is 3, straight is 1, padding is 1. So we get is input length is 10, and the kernel size is 3, straight is 1, padding is 1. So it's just 10 plus 10, the input length 10, and more plus 2 of the pattern. Pattern is 1, so it's 2. And then minus 3. 3 is the K, the kernel size. And then the 1 is the stride. So it's 1. So it's 10 plus 2 minus 3 equal 9. And 9 divide 1 equal 9.
There's the
Where? What do you use? Oh.
Sorry, guys, we have a minor tech issue with the projector, so we'll be starting in a second. I think it did connect. It's just taking, so the projector has to warm up,
Okay.
right?
Okay. Okay, let's continue. So it's 9 divided 1 equal 9. And then 9 plus 1 equal 10. So the output length is 10. Another thing I need to say is we cannot put the stride equal 1 and padding equal 1 here. If we don't set the stride, it will equal the default is 1. If we don't set the padding, the default is 0. So the first axis, if input shape 8 16,2048. And then go through this convolution. What is the output side shape? Yeah. You guys can try this.
You actually be able to pass the input with the convolution, because the number of channels in your input does not match in channels in your convolution.
Oh, you mean in channel and output channel is not match?
No, yeah, I mean, in conv D, you say in channels is 8, but in your input shape, you say there's 16 channels,
Oh,
right?
oh yeah. Yeah, here should be
Okay,
8.
so they should just match.
Yeah. Here should be 8.
Five hundred. 864, 511. 64.
64 and then
511.
500 is. Yeah, you're right. Yeah. Did anyone get this result? Everyone get this result? Okay, next one. Okay, this one is a little harder. The X2 is if we import shape is 430 to 1024. And then it will go through 2 convolution layers.
I got 4,128 and 169.
And then
128 and 169.
169.
Yeah.
Wow, you're so good. It's Reggie.
Yeah.
Has anyone finished the exercise? Okay, here is a thing I didn't show here, but I will talk about. So let's say the input, the actual number is 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. And the kernel is looks like this. And then the convolution is looks um, kernels fine. Of course, I could try this. Try. Good. So let's say yes, and okay. So x equal 0. Okay, let's say the input, the actual number is 1, 2, 3, 4, 5, 6. The sequence is data. If the kernel filter is looks like 1, 0, -1, the bias is 0.2. So the output is should be looks like. So let's say the first one, the first kernel is will cover the 1, 2, 3. And kernel size looks like this. So it will looks like 1 multiple 1, and then 2, and then plus, no plus, and then 2 multiple there. Yeah, it should have 2 multiple 0, and then 3 multiple -1, and then it should be equal 3 or 1, and then equal -2. And then since its bias is true, so we need to add the bias. So let's there. And then the second one is 2, 3, 4, and then the kernel's matrix 2 is this. So it's 54, and then it so it will equal -2. -2, and then it need to add bias again. And then the third one should be, and then the matrix picture is like this. So it's a 3 plus 0 equal 2. So it's also like this. And then the last one is So this is how actually the convolution works. It will like multiple the kernel matrix first, and then add the bias. And then it will output like this. So this is how the convolution calculates. And then is polling. Polling is a non-learnable operation in deep learning that reduces the spatial or temporal resolution by summarizing local regions, typically using max, average, or mini values. It's just like this picture showed. So the first three will choose the biggest one. The second also choose the 5 as biggest one. Every kernel will choose biggest one instead. So this is how the post length calculation looks like. The input length minus the kernel size, and then divide the stride of that, and then plus 1. So the other thing I need to talk is in the poll you also can use the padding. Yeah, you also can use padding to make sure the length is the same as the input. It's like importing. You don't have to like reduce the length. So if you want to do that. Another thing is in the max poll or average poll. If you only define the kernel size equal 4, if you didn't define the stride, the stride will auto equal the kernel size. So if the kernel size equal 4, it will just reduce the, just like here say, the input length is 16, the kernel size is 4, the stride is 4. We don't have to define the stride. You can just don't define it because the method will auto make it as the kernel size. So if it's 16 and then minus 4, divide 4 plus 1. So finally it becomes 4. The length will become 1/4 long compared to the import part. So the exercise 3. Okay. So the exercise 3, if we import is 2, 16, 50, 50. So it will be 50 minus 2 minus 2 and then divide 2 and plus 1 equal like 40 equal 48 divided 2 plus 1. So it equal 25. So the final length it should be 25. Yeah. And then the exercise 4 is the max pull on a specific data. So we will give input tensor, the length is 10. So this is how the tensor looks like. So you need to use the pull or max pull kernel equal to stride equal to get the answer. The way to calculate this, just like this picture. So this one is like kernel 3. So you just choose the biggest. So if it's kernel 2, it's just 1 and 2 and choose the 2 instead. Yeah. Okay. Okay, so let me show how to solve this question. So it's a max 4, and then the kernel size is 2. So it's like 1, 3. We choose 1. So it should be 3. But the stride also 2 means it will skip this 2 to 5. So in 2, 5, we choose 5. And then in 4 and 7, we choose 6. So we choose 7. And 8 and 6, we will choose 8. And the last one, we will choose 1. Oh. Oh, there we go. It's 1, 2 is 3, 2, 5 is 5, 0, 4 is 4.
I got 3, 5, 4, 8, 6.
Yeah. Right. Okay, and then the next one is the XS6. So we will calculate the average pole on the specific data. The average pole compared to the mass pole is just like let's like here say the kernel size is 2 and stride is 2. So 1 and 3, we just average them. So the first one will be 2. Yeah. So and to next part. So the average is just average. Okay, we'll show how to solve this question. So since it's a average pole, and kernel size is 2, stride is 2. So 1 plus 3 divided 2 equal to 2, 5. The average is 2.5. And then 0 and 4 equal to
3.5, right?
Hmm?
It's going to be 3.5, right? Take the average of 2 and 5. You take the average of 1 and 3, then 2 and 5.
What?
You first take the average of 1 and 3, then 2 and 5. And
Yeah.
The average of 2 and 5 is 3.5.
Oh yeah. I'm sorry. Yeah. Should be 3.5. And then 0 and 4, the average is 2. And then 7 and 8 is 2.5. And then 6 and 1 is 3.5. Should be this one. Yeah. So this is how to solve this. Okay, so after we talk about convolution and pole, convolution is to do a learned weight, and the pole is try to extract the feature. But right now we will talk about normalization. In general, this is four normalization we will use. The first one is the batch normal. Batch normal is it will normalize through the whole, like let's say the batch size 8. It will normalize in these 8 samples. And then it will normalize through each channel. So it makes the batch size is very sensitive about the batch size. If it's very small, it will not work. In general, if you want to have a very stable result, you need more than 32. So in general, it will use for CN. Yeah, it need a big bag and need a large batch size. So the batch size will learn through each channel per channel. The layer normal, it will normalize through each sample. So it's like channel, height, and width, it will normalize together. So since it's not based on a lot of batch size, so it will be more stable. If you don't have enough data and your laptop don't have strong performance, so you have to do like batch size equal 4. The layer normal will be better than batch size. So right now, in general, it will use for the transformer RNN, like sequence model, and also used for the MLP, the full connect layer. The group normal is just the batch normal, but it will not go through per batch. It will just only normalize through each sample. So it's okay for use for like CNN with small batch size. Yeah. And then another one is instance normal. Instance normal is just like you state like group them like 3, and then it will normalize through this. It's just the instance normal and have like a little more. Yeah, it's used for style transfer, image generation. Yeah. So in general, when we build a model, the most used is batch normal and layer normal. And then right now is activation function. Activation function will import the unlinear to the model. Because not all the things is like linear, so we need to import some things unlinear to get the better performance. So first one is RELU. It's like this. So if it's negative, it's just so it's only like from 0 more. So it's positive. So advantage is it's very simple and fast. And it's good for the positive gradient. But its advantage is, so you can see here. So if something is negative, it will just become 0. It will cause the dying arrows. In general, we'll use this on the CNN or image classification. And then it's also like computation is very low. Another one is leaky RELU, and it's just an improved version of RELU. It like fix the dead narrow issue like here. So it will import a little place for the number which is more than 0. So the disadvantage is like it will cause the slight noise from negative slope. Yeah. And then the ELU is this one. So it's smooth. And then you also allow the negative values, and then it has the better coverage. But it needs alpha. Yeah, and then usually it's used for the detonates, and then it can also like avoid the dying arrows. You can see it's like almost like an improved version or ELU. And then it's a sig mode. It will output like from 0 to 1. It's like so it's good for like a probabilities. So in general, if we will do some regression, we will have 1 on the end. If your output is like it's not negative, it's like from 0 to 1, like the predicted redshift, it will be good use sig mode at the end. The disadvantage is like saturates easily and it's slow. It's non-zero centered. The TANH, the advantage is 0 centered and it has a smooth output. It's this. And then it's also has the issue like saturate the large inputs. In general, it will use for R and or sequence models. The GLU is a most non-linear get performance, like it's very good in like the transformers. Yeah, transformers will use GLU. It's complex, it's slower than the Argyro. Not only the transformers, like some right now, and some like the more modern CNN, like the large model, it will use GLU to have some similar idea like transformer to like improve the CNN models. Switch is a learnable gate. It's smooth and better than Argyro in some case. But inside it will use mode. It's a little bit slower. Mask out, it can learn any convex function, avoids vanished gradient. But it has some issue. It's the parameter heavy and it's very expensive to train. Yeah, it is some like the normal common deviation function looks like. After that is a regularization. In general, we will use dropouts. Dropout and prevent like the overfitting. Like we can cut here, just like these pictures. Can make sure like we will randomly cut some branch. It can prevent the overfitting. Yeah, like in general, we will use this during the fault connection part to make sure the model is overfitting. Another one is drop pass. Drop pass, we will not use this during the like very simple convolution. But if we use for some like the deep network, like they will have a lot of blocks, like the ResNet or like the ONNX. In this kind of modern CNN model, they will use skipping connection. They will use skip connection to have a better accuracy. But this kind of model, because it's so complex, it's easy to overfitting. So in general, people will drop pass. Drop pass is like it will, because this kind of modern model consists of a lot of blocks, the same block stacked together again and again. So it will drop the sum of the block, just drop all the block. Yeah, this two is both is for like prevent overfitting. So another one is the linear layers, or we call it a fully connect. The linear layer is a core component in neural networks, often used after feature extraction to filter information globally or map it to the output space. Just like in CNN, we will use convolution and pole to get some local features. And then we will flatten the linear layer will make it output to your target. So the full connected layer will perform as a learnable frame transformations. The efficiency like this. So if you want to use that, it's like the info feature, like we extract from the convolution, like we get like 256 lengths, and then we can use linear to make it output to like 10 class. Yeah, we will use the linear at the end of your model. So this is how a network looks like. So the first is the feature extraction layer. we will use convolution to extract the local features. The polling will downsample and reduce partial size. And then we will use the normalization to stabilize the training, the batch size and normalize. After that, we will use activation to introduce some non-linearly information. And then maybe we will also use dropout if you feel like it's too much overfitting. So you can also use dropout in this part to prevent overfitting. After that is the FC layer. We call it a fully connected layers. So first, after we extract from the data, there will be have like a channel like as like a 32 channel. The length is like 64. We can't just put them in a linear because linear is only accept for the like one dimension. It's like a line. It's like a line. So we have to flatten the feature we extract. So it will become a one big vector. After that, we will use linear, the performance global. And then you also can use the activation in here for the non-linearly. In general, here's normalize. In general, we will use layer normal. It will be more stable than the batch normal. In general, we will also like add a dropout or like add two. If you think it's still too much, you can add a dropout in each layer. In general, the fully connected layers will only start. The max is like three linear layers. In general we will not add more. It will just cause the overfitting and make the model remember some of the data. Actually, data, not the yeah. It will just cause the overfitting. So in general, you shouldn't like use like more than three linears. So after that is the output layers. Yeah, for the classification, it can produce like budgets and or probability stores. For regression, it will output the continuity values. Yeah. And we can take a break here.